So, example 21. I think my picture's cool. Julian, is that picture cool? It's all right. Good. All right. So here is the astronaut moving away from the space station because the explosion happened. And yes, an explosion can happen in space as long as there's available oxygen to burn. So we'll say one of the oxygen canisters ruptured. There you go, Kevin. You got your reference now. All right. So she's moving this way. She wants to save her life, so she throws the tool, right? Right. So this is a conservation momentum problem. Okay. To start out, we have the mass of the tool plus the mass of the woman plus the mass of the spacesuit, right? Times the velocity, right? Equals mass of the tool times velocity of the tool plus mass of woman plus mass of spacesuit times hopefully her life-saving velocity.
That's where I get confused. Like, I don't know what mass is where.
Whatever is moving together in the same direction with the same velocity, have those masses be added together. So initially, all three things are moving with the same velocity in the same direction, right?
No, not that. Like, I'm talking about when you put like
Right.
mass, T,
Right. After she throws the tool, just the tool is moving at its own a different velocity, right? The woman in the spacesuit are still moving at the same velocity. So if two objects are moving in the same with the same velocity in the same direction, Sergio, then add their masses together. All right. So we can start plugging in what we know, but before we plug in what we know, let's think about this for a second. In order for the woman to save her life, her velocity has to go from positive, pass through 0 and become negative. Okay, we're gonna call this way the positive direction since we have the point 4 is positive. All right? So her velocity has to pass through 0 and become negative. So to figure out the minimum velocity required, what should we have her velocity be? 0. Okay? Because we could say 0.0000000000001 would work. Right? It would start moving her back towards the spaceship. Or the space station. Alright, so let's have it be 0, and we'll adjust accordingly at the end. Alright, so let's plug in what we know. What's the total mass? 102. 70 plus 25 is 95, plus 7 is 102. What's the initial velocity? 0.4. Okay. Final velocity of the tool. Or sorry, mass of the tool. 7. Do we know the final velocity? No. Plus her mass in the spacesuit? 95. And we said that V was going to be 0. And this will help us find our minimum velocity required. So 102 times 0.4? 40.8. Equals 7 VT, right? So what do we do now? Divide by 7. That T is terrible. Divide by 7. 40.8 divide 7. 5.82. So, if she throws the tool with a velocity of 5.82 meters per second, right? 5.82 meters per second. Then this will stop her momentum, right? Right? Then her final velocity will be 0, so she will stop. So in order to get her to move back towards the ship, right? Should she throw the tool with a greater velocity than 5.02 or a smaller velocity than 5.02? Tony, you said greater. Why greater? Okay, so we can pass through 0. Okay. Richard, why'd you say greater? Okay, so we do smaller, she'll keep going in the same direction, right? Because right now she has positive momentum going that way, doesn't she? She has a positive momentum of 40.8. I want her momentum to be going back that way, don't I? So if her momentum is going back that way, that means the tool's momentum has to be greater than 40.8, right? In order for the tool's momentum to be greater than 40.8, the velocity has to be greater than 5.82. Because Because when the velocity is 5.82, the momentum is 40.8. Right? So the velocity is greater. So any velocity greater than 5.82 will work. Does that make sense? That make sense, guys?
It's 5.83.
5.83? Okay. Any questions?